Good afternoon, everyone. Thank you so much for joining us. I'm Rebecca Rodriguez. I'm the director for the NIDDK Central Repository. And for those of you not familiar with the NIDDK Central Repository, our program was established over 20 years ago to facilitate the sharing of data, specimens, and other resources with the broader research community. Next slide. Since 2003, we have facilitated the receipt and distribution of data and specimens, ensuring that these are shared ethically and efficiently with all qualified investigators. We have empowered countless of researchers to test new hypotheses without the need to gather new resources and continuously strive to promote fair and proudly fair and trust principles, and our repositories among a handful of NIH control access repositories. We proudly hold the prestigious Core Trust Seal certification that indicates our user community that we meet the desirable characteristics of data repositories. Additionally, we are members of the World Data Systems, reinforcing our dedication to best practices and data sharing principles. Our collections include over 15 million imaging files and more than 8,000 clinical data files from about 186 studies available for request. We have over 60 million specimens, with more than 60% of those currently available for request by the external research community. Our user base continues to grow with over 6,500 registered users who have produced more than 800 public releases, of which about 200 are searchable on our website. Next slide. The repository is part of NIDDK's broader data sharing ecosystem and is key to NIH fairness and trustworthiness goals. We house a broad range of resources and provide linkages to resources stored outside the central repository. These help us support our users in achieving their multimodal research aims. Next slide. As you may know, we're continuously modernizing our repository infrastructure to enhance our services and features, and in the coming months, we plan to deploy our cloud-based analytics environment, allowing clinical researchers and data scientists to access a suite of integrated analytic tools and cloud computing resources. This will enable them to participate in and conduct data challenges and drive AI innovation, which I will elaborate in the next slide. But for this analytic workbench, this promises to streamline the data science lifecycle and facilitate the discovery of data-driven biomedical insights. We anticipate that the platform will increase collaboration, minimize data movement, improve user experience, and more importantly, advance the research missions of NIH and NIDDK. Next slide. As mentioned, I wanted to speak a bit about our Data-Centric Challenge series, which we launched in 2023. This series aims to develop tools, approaches, and models and methods to increase the interoperability and usability of data for AI and ML applications. The series was designed to build on one another, where each challenge and challenge participants are tasked with developing innovative approaches for augmenting and enhancing existing central repository data, improving their utility for future secondary research, including data-driven AI and ML discoveries. I encourage all of you to visit our website for information on past and future data challenges and to join the data-centric movement. Next slide. As you may have guessed, as part of that, on the last Thursday of every month, we plan on conducting these webinars with the goal of accelerating data science and AI-driven biomedical research and fostering collaborations between biomedical researchers and data science experts. I hope that you continue to join us. These webinars will also serve to prepare potential participants for future data challenges. For more information on the webinar series, to view past recordings, and to register for future events, please visit our website. Next slide. And now I want to introduce you to our experts for the day, Erica Christensen and Dr. Gordon Ayala. Erica serves as the lead associate data scientist at Booz Allen Hamilton. She holds a bachelor's degree in industrial and systems engineering from the University of San Diego. Her expertise lies in natural language processing and supervised machine learning. Erica contributed to the Raven project at the Naval Information Warfare Systems Command. Currently, she assists the Chief Digital Artificial Intelligence Office, where she focuses on developing dashboards and data pipelines to assess risks and resilience for sailors at both the individual and unit levels. Moreover, she heads the Data Science Learning Program for the Naval Information Warfare System Command to deliver training across the Navy in data science, machine learning, and artificial intelligence techniques. Dr. Ayala is a lead scientist at Booz Allen Hamilton, and he holds a PhD in applied mathematical and computational sciences. He focuses on developing and delivering specialized training in data science, artificial intelligence, machine learning, and Python for clients in the Navy and the intelligence community. Before joining Booz Allen Hamilton, he worked in the Office of Microeconomic Affairs at the U.S. Department of State, employing machine learning techniques to analyze developing and emerging markets economies. He also taught courses on data science and R programming language for the Foundation of Advanced Education in Sciences at NIH. He's passionate about collaborating with others to enhance their understanding of data science techniques and their applications. So I provide them with both a warm welcome, and I pass it on to you, Erica.
Perfect. Thank you so much for that introduction. I will take over screen sharing. Can I get confirmation that you can see and hear me?
Yes.
Okay, perfect. Thank you guys so much for being here today. This is one of a couple of trainings that we'll be teaching. The first one is Data Science Fundamentals, and I am happy to bring you through the next couple of hours of training. Some just initial training guidance. We have a lot on the line, so we definitely want to encourage conversations. We'll have some time for you to come off mute if you have questions that you'd like to ask. We have a short 5-minute break partway through this training, as well as time that's dedicated for questions at the end here if you want to come off mute and ask your question. But we definitely encourage chatter and questions in the Teams chat, and we'll have the other instructor on the line, Dr. Aiello, to answer those questions when I'm speaking if I'm not able to get to them. And we already did instructor introductions. I'll be going first. It's great to be here today. And this program, as mentioned in my introduction, I work for the NAVWAR 4.0 Data Science Learning Program, and it's really expanded outside of NAVWAR to all Navy systems and syscoms. And we teach a series of trainings, Data Science Fundamentals being one of them. And in today's course, we'll bring together a couple of topics from different courses that we teach to bring you through Data Science Fundamentals. So the agenda for today, we're first going to cover the data science process, what that looks like, and then we'll go into supervised and unsupervised learning techniques and take a deeper dive into what those mean and how those look in practice. Then we'll be covering some deep learning techniques, as well as specialized data science topics, things like computer vision, time series, and natural language processing. I will say in future seminars that we'll be having in March and April, we'll be going in a bit deeper, especially in the deep learning topic. So if that interests you, I definitely recommend signing up for our next webinar. So first, we'll be starting with the data science process. So I'm going to put in a question chat, actually. And if you just want to use the like icon, if this applies to you, I have a lot of experience with data science, AI, and ML techniques, whether you've learned a lot about it or you've used it in practice, or I don't have a lot of experience. So either one is fine, just like the statement in the chat that applies to you. We'll be covering, starting at the basics, of course, with data science fundamentals, but just like to get an idea of who's in our class, what experience that they have. I'm totally okay either or. I'll give a few seconds for that. Okay. So I think we're leaning more towards not a ton of experience with data science, but whether or not you have experience or you don't have experience, hopefully you can take something from this webinar series. But we'll definitely start at the very beginning and work off from there. Okay. We want to go to the first statement in data science and really start to define what that means when we refer to what is data science. So for the purposes of this course, we are going to define data science as the goal of data science is to extract meaningful insights from data. So breaking that down further, we can take data, or component data, which can be defined as any kind of qualitative or quantitative sets of values. And data can come in all shapes and sizes, right? So we have natural text, categories, numbers, images. Sometimes you have the data, sometimes you need to procure it. It can also look all types of ways. You can have structured data or unstructured data. And when you combine that with science, we're thinking the systematic approach to building knowledge by testing hypotheses. So think of the scientific method, where you define a hypothesis, you collect the data, you perform an experiment, and ultimately you prove or disprove your hypotheses. So that same system is applied in data science when we combine those together. Data science can be a larger or broader field that we think about. But when we say terms like artificial intelligence or machine learning or even deep learning, those are all different subsets of the larger, broader field of data science. So we define data science extracting meaningful insights from data. But when we look at what AI is, which is a subset of data science, AI is the theory and development of computer systems able to perform tasks normally requiring human intelligence. So another way of saying this is that AI uses tools to mimic human problem solving and decision making. Common applications of AI include things like natural language processing, image analysis, the development of autonomous vehicles and robots. It's a broad definition, and it's meant to be broad because the applications of artificial intelligence are constantly changing as our computer resources and our technology increases. I like to think about when the calculator was created. The calculator could have been considered AI of that day, right? Because before calculators were created, it actually took a human to sit down, perform those computations to give you results. Once a computer system of the calculator was introduced, it took the human out of the loop, and it was now a computer that was able to perform a task that normally required human intelligence. Of course, now we wouldn't think of a calculator as being AI of today. We're much farther than that, but it is like a broad moving field of what can be considered AI. And then one subset further, an application of both data science and artificial intelligence would be machine learning. So we're going to outline the machine learning process in just a minute, but for now we'll say that the machine learning process is focused on understanding and building models that learn from data and leverage real-world observations to improve the performance on a given task. So another way of saying this is that it uses algorithms and statistics in a way that imitates how humans learn. So machine learning, we'll see that eventually you're trying to gain a prediction, and your machine learning algorithm will learn about your historical data, ultimately to give you some sort of prediction. So here are a few examples in the commercial world of where you see data science popping up all around you. It is more common than ever, but the purpose of these slides is just to really highlight the current capabilities of AI and get you thinking about what potential applications that you may commonly see around you. You've probably seen all of these before, but first we have the Amazon recommendation system. This leverages recommendation engines to guide customers to specific items. So things like customers like you also purchased, or because you purchased nails, do you also want to purchase a hammer? That is an AI-powered research engine that is essentially building out a profile for you and trying to make you buy more. We also have a credit card fraud detection. So this also is building out a profile about you to learn about what your behaviors are and what your regular buying patterns are. So then they can use this information to detect anomalous activity or transactions on your card. Are you randomly in a different country and you didn't use it at the airport before? Did you make a really large purchase that's out of your normal pattern of behavior? So it can start defining what is detecting as fraud. Some of the more popular example, ChatGPT, of course, that was released in 2022. And now they have iterated a couple of versions of this, but this is using natural language processing and some deep learning methods, transformer methods, to essentially be trained on the entire internet and actually generate new data. So it's a new subfield, a relatively new subfield, where instead of just predicting on data, let me take this off. Instead of just predicting on data, it generates data that's never been seen before. So if we actually go back to this slide, you can see here it says computer generated. This was a generated image using an open source platform to create image of Winnie the Pooh. And that was an image that's never been seen before. And it's taking the prompt and actually creating that image. We have Snapchat and other augmented technologies. So this is actually taking in a video stream or a picture stream and augmenting the space around you. We also have a lot of voice recognition systems like Google Voice or Amazon Alexa, and this also uses natural language processing techniques to detect, interpret, and respond to audio prompts. And then finally, we have UPS. This is an optimization navigation route where it uses machine learning to optimize package routing, and it updates in real time. So it's designed to support both drivers and customers by reducing delivery time, miles driven, and fuel consumed. So this is data science in the commercial space, but of course we have data science in healthcare as well. So things like predictive analysis for early diagnosis. This can be using things like tabular data, like an Excel or CSV data set, or even things like imaging data. If you're viewing scans and you're predicting, if someone has a specific disease or a specific illness using their features of health. We also have been seeing personalized medicine. So getting a machine learning model to tailor treatments even more fine-tunedly than what maybe doctors would prescribe based on a larger portion of their history, like genetic profile, their lifestyle, their medical history. And this can work hand in hand with the doctor to come up with a treatment plan. Early detection and progression monitoring of kidney disease. We've seen a lot of machine learning efforts or artificial intelligence efforts being built around early detection. Can you use machine learning to help analyze imaging results, lab results, to detect key factors in certain diseases that would not be picked up before? And then, of course, diabetes prediction and management, using machine learning models to analyze patient data once again, including different levels like glucose or lifestyle factors to predict diabetic risk, and especially get that early detection so you can start treatment maybe with a personalized medicine plan before. So now that we've seen some applications of data science, AI, and machine learning, and where they may pop up, and why it's so useful to have this come in handy, we are going to walk through first the data science process. So this graphic illustrates the data science process that we like to go by. These steps are loosely derived from the scientific method that we outlined on the previous slide. The ultimate goal, of course, is deriving those insights from your data and turning it into actionable outputs. And we find it useful to divide projects into these 7 steps. I will note, if you look this up online or if you ask a data scientist, some of the steps could be different or different paradigms could be used, something like CRISP DM you may have heard of, but all of the steps are essentially the same that we'll walk you through today, where it outlines problem statement to data acquisition, exploratory data analysis, data prep, modeling, visualization, and taking action. In practice, problem statement to data prep will take the majority of your time. It will take around 80% of your time before you get to what we call the fun part, modeling, visualization, and of course, deploying something. We'll walk through what each of these steps look like and some key components to start thinking about. This is just a descriptor of what is contained in each of these steps. In the problem statement, you're going to be forming the SMART problem statement. In our second step, we will actually acquire our useful data that can assist in the problem statement. Then we'll explore and understand our data, prepare the data for modeling. Then we'll actually model. We'll render visualizations that are helpful to output the story of our data, and then we'll take action. Now, although this is written out in a very linear format, most often it's not linear. You are consistently going back between each of the steps to figure out maybe you don't have enough data when you're exploring it. You need to go back and collect more. Or maybe you use a machine learning model and it's not performing to the threshold set, so you need to go back and prepare your data more. So it's very iterative, but it's helpful to think about it, in 7 discrete steps. So our problem statement that we'll be covering first here. A data science project should begin with the formation of a good problem statement. So one thing to keep in mind when designing this problem statement is data science is not magic. It cannot answer every question under the sun. So we want to go back to what data science can answer. And data science is based on all mathematical and statistical techniques. So it's going to limit the types of questions that can be addressed in this field. So at a high level, you want your problem to be both structured and attainable. And in addition, the problem needs to be specific and relevant and unambiguous. So to further narrow down the types of problems that are good fit for data science, there's outlines a list of questions that can help guide this process. Things like, what do you ultimately want to predict or estimate? Are you predicting a specific label for a category? Like, does this patient have a disease or not? Or are you trying to predict a numeric value? What is the glucose level of this patient? What is the end goal for your project? What are you trying to achieve at the end of the day by solving this problem? What would be the value added to your work? Is it worth pursuing this project, especially one that could be time intensive? Sometimes the right decision is to not pursue a data science project if the risks or resources cost outweigh the potential value that it may provide. What would you do if you had all the data? How difficult would it be to obtain that data? Who owns the data? Is the data source trustworthy? And what patterns do you think are relevant? It's important to know what you're looking for before embarking on a new project. So this may require the involvement of a domain expert or a subject matter expert if you are not that person. And it's definitely okay if you're not that person. I'm working in a Navy field, and I'm not familiar with Navy data sets. So I have to pull in subject matter experts to help me give an understanding of what this data set means, what the process currently looks like, and how could a data science solution help the process at hand. So to help us organize all of these questions and considerations, we can utilize what we call a SMART framework. SMART stands for specific, measurable, achievable, relevant, and time-bound. And this is the guide that we like to outline all of our problem statements. And at the end of this, we hope to create an attainable project or an MVP, minimum viable project, that we can then stand up. SMART goals, of course, aren't specific to data science, but they are very useful in data science to make sure that we are making an attainable goal and not shooting for the moon. So one way of thinking about a SMART goal setting is to imagine this funnel. So you work through each step of the SMART framework in sequence, and your goal is to move from being very broad and vaguely defined to very narrowed and focused. It's much easier to answer a very narrowed and focused question. And this process is designed iteratively to refine your problem statement to ensure it remains strategic and on point. And then we'll go through each segment of the funnel in more detail over these next few slides to use an example use case to guide our conversation. Let's go with a SMART goal here. So one way or a SMART problem statement we could think of is researchers seek a data-driven approach to better understand the factors that are most strongly associated with a chronic kidney disease. The aim of this project is to develop models using clinical patient data to accurately predict chronic kidney disease. So for the rest of our data science process, we'll kind of go back to this goal to see, what steps that we can take to help achieve this. We have this overall statement or objective that we're trying to achieve, use a model to predict chronic kidney disease. Now kind of writing it out into the actual SMART framework. So specific, we want to train a machine learning model using clinical patient data to predict who's at greatest risk for developing chronic kidney disease. Measurable. This is our threshold that we'll set. In our case, we want to target it to at least 90% accuracy for predicting when patients have this chronic kidney disease. Attainable by leveraging existing data sets that are available and proven analytic capabilities. We'll work with resources available to the NIH. Reasonable, the models will help researchers and medical providers make objective, data-driven healthcare decisions, highlighting insights that may be currently overlooked. And time-bound, the models will be developed, validated, and ready for deployment within 6 months, with a prototype ready for review in 3 months. Very important to time-bound this project to at least get something working, and then you can always iterate on it after. Data science projects, again, can be time-intensive, so trying to figure out what is the minimum viable product that you can stand up to prove some success before you maybe add in other use cases or stretch goals to your project. So we've looked at the SMART problem statement: specific, measurable, attainable, already forgot it, specific, measurable, achievable, relevant, and time-bound. And then we'll move to data acquisition. This is the second step in our data science process. Once we've defined a problem statement, we'll move to acquiring our data. So one of the terms you may have heard of is big data, or the idea of big data. There's no standardized definition of big data, but it's widely agreed that all big data sources share some common characteristics here. They are sometimes referred to as the 4 V's of big data. Note that while your particular project may or may not be working with big data, these concepts are important to have working knowledge of. So we can take a look at volume, velocity, variety, and veracity. Volume, as the name suggests, implies that your data set is large. There's no clear threshold of what a large data set looks like, but you can expect to measure the data in terabytes or even petabytes. Velocity means that the data is being streamed, processed, and analyzed at high speeds. This typically requires uses of high processing powers or GPUs to work with the data. Variety implies that the big data brings together a diversity of data sources, and each data source may require different sets of processing techniques. And finally, veracity refers to the consistency, accuracy, quality, and trustworthiness of data. So this is a big one. The guiding principle here, the phrase is garbage in equals garbage out, which we'll touch on. But when we discuss data preparation, we want to make sure that our data is trustworthy and it is of quality, because what goes into our model is what's going to come out of the model. So you want to gain that trust with your end users that your model is predicting accurately at all times. And so you want to make sure that the quality is up to par. So data comes in a variety of forms. So regardless of the size, you can broadly divide all data sources into two types: structured data and unstructured data. Structured data refers to data that is highly organized and fits into predefined fields. So think of a tabular format, CSV or Excel, and then the items in the structured data set would be like ID numbers or dates, names that can appear as columns within your tabular data set. If you have unstructured data, this will differ that it cannot be easily represented in a tabular format. So some common types of unstructured data that you may encounter include things like photos, video, audio files, PDFs, emails. All these different data types share common characteristics that they are not typically stored within something like Excel. There's different ways to organize these data sources, but they require a different approach and storage mechanisms to work with this data or potentially put it into a structured data format so then you can begin to analyze it. So we discussed it in a binary category, structured versus unstructured. If we wanted to be super technical about it, we can also have a semi-structured data set. But each of these data sources, we probably work with a combination of all of them in our day-to-day, and they may or may not be useful to us when we're starting to look at which data that we have access to or which data that we need to get access to and how they're stored. You can work with all of these types of data in your data science process. It just is how you're going to acquire it and format it so you can prepare it for modeling is what differs. So if we go back to our kidney disease example, we can think of this data source. It was sourced from UC Irvine's machine learning repository, open source data set, and there is columns in here. It's a tabular structured format. So we have things like the ID number of the patient, the age of the patient, and then several other columns, their blood values, and including the classification. Do they have kidney disease or not, or chronic kidney disease? This is just a snippet of the data dictionary. It is always helpful to have a data dictionary with you. Most oftentimes, they're not already created, I have found. So it's helpful as soon as you start working on a data source to create a data dictionary. What are the columns names and what do they mean? This is really helpful if you're working with a team, so everyone has a shared understanding of exactly what's going on in each of the columns. So for our case, we have age, blood pressure, sugar, red blood cells, and then that classification. This is ultimately what we'll want to predict. According to our problem statement, yes or no, do they have a chronic kidney disease? So we have acquired our data, and now we'll move to exploratory data analysis. The end goal of exploratory data analysis is to understand our data set. So the purpose of this cartoon is to illustrate that we are going to need a broad view of the data to do this. So each of these people examining the elephant, they're examining a very small portion of it. It's a fan, it's a wall, it's a rope, it's a tree, and they're all correct, kind of, in their own examination of what that data or what this object in front of them is, but none of them are taking a step back, looking at the entire data set or the entire object for what it is to really get a better picture. A guiding principle here, the saying is missing the forest for the trees. So just like these people are miscategorizing an elephant by examining each body part in isolation, it's possible to miss key facts about the shape, the distribution of your data set by evaluating a small handful of analytic metrics. So you need to put them in a broader context. And we can do that through different ways of analyzing our data. So there's 4 different types of main analytics: descriptive, diagnostic, predictive, and prescriptive. The key takeaway here is that typically the more advanced an analytic technique is, the more potential exists for adding value to a given project. So the most basic form of analytics is descriptive analytics. So it's leveraging our measurements to outline what has happened. You're describing your data set. So it's a great place to start very low in complexity, but also doesn't add a ton of value to your overall project. Moving to diagnostic is asking yourself, why did it happen? This subset of analytics is interested in finding root cause of why something has occurred. And then when we get into predictive and prescriptive, this is when we start jumping into kind of like our machine learning realm. Predictive is asking what will happen. So looking at lessons learned from the descriptive and diagnostic analytics to attempt to predict a future outcome. And then prescriptive represents the most complex to actually perform, but perhaps the most added value. And this is the focus on setting the goal of how can we make this happen, or how can we ensure that this does not happen? So there is 4 different types of discovery when you are looking at discovering your data set. So the first is class discovery. So when you're looking at your entire data set, you're identifying potential categories of objects or population segments, different events or behaviors within your data set. One application of this discovery is to allow you to report statistical findings for both the entire population as well as for different subgroups within your population. Outlier is as it sounds. It's identifying new and surprising objects, events, or behaviors within a population. So this is critical since many machine learning models and data visualizations are very sensitive to outliers. So identifying potential outliers early could be an important step in building stronger models. Maybe your outlier is something that you want to key in on. You want to find when those outliers are occurring. Or maybe outliers are actually, a dirty data set, or it's non-quality, where in your data you have an outlier. Maybe the system failed, and it's reporting a bunch of null values because that system was turned off, for instance. So figuring out what those outliers are and how you want to handle them. Correlation discovery is about finding trends and patterns and dependencies in your data. So this is an important step when building your machine learning models. We're not going to go in depth on the underlying mathematics, but we will look at some of the correlation in our data set on the next slide. And then finally, association discovery involves finding data association, links, or connections within your data set. This is for a broader view of the data, looking at potential linear relationships surfaced within correlation discovery. For example, association discovery could involve reviewing the time series data to look for trends and seasonality within your population. So we touched on correlation discovery. And this could be an example of this. So if we pull up our data set of the chronic kidney disease, this is actually a snippet of code. This is the first time you've seen Python, fear not. It is very simple, where the most important line here is just pulling up this function that we're calling, and we're asking it to apply a heat map to our data set and calculate the correlations. So this will be a heat map of our entire data set, where really lightly colored will be a positive correlation versus very darkly colored will be a negative correlation. So it's very helpful when trying to determine a target variable. You can look at what's correlated with one another. And we have like packed cell volume compared to our hemoglobin, which I'm going to find. Hemoglobin packed cell volume is a 0.9. So those are very highly correlated variables, which maybe makes sense. The packed cell volume is the measure of proportion of red blood cells, and your hemoglobin carries oxygen throughout the blood. So if you have more hemoglobin, you also have a higher packed cell volume, and vice versa. So that's what that means, at that 0.9, it's very highly correlated. So this is one way you can start to discover information about your data set through data science. Another plot here. This is a violin plot using a package in Python called Plotly, and it's showing on the x-axis zeros or ones. Our 0 is our blue violin plot there, and that means they do not have a chronic kidney disease. And 1, that red plot, is showing that they do have a chronic kidney disease. and it's showing the red blood cell count. So values shown on the y-axis are also showing the maximum, minimum values, as well as the quartile values when you hover over the plot. So this is just a screenshot, but you can hover over it and you can see the maximum and minimum and different descriptive statistics about your data set. But if we compare no chronic kidney disease compared to chronic kidney disease, we have a much higher red blood cell count in those that have chronic kidney diseases. So we've begun to explore our data set through different techniques and class discoveries, and now we'll move to preparing our data. I've mentioned before, it's messy. It's never going to be clean cut, even if it's coming from sensor data or people's inputs especially. There's always going to be work to be done to make sure that it is this quality. And rule of thumb, 80% of your time is spent on data preparation and probably exploring your data and actually acquiring your data. And that 20% represents machine learning, visualization, and taking action. So you should expect kind of a large amount of workload in the beginning. Because our data is dirty, especially with the veracity in which we're receiving data and collecting it from all different types of places, dirty data can be everywhere. So things with typos or errors, missing data, null fields, you have different labels for the same item. You're referring to something, but it's spelled differently in different columns or in different rows. Duplicate entries where there shouldn't be, entries that don't match up with another data set where they should, and a lot more. And these data entries can skew the outcome of your models. And we'll look at that in a slide that's coming up here. So looking at our descriptive statistics just of our open source data set. So this is also showing another snippet from Python. We have just interjected these throughout the course just to see what it can look like if you actually deploy a data science process using Python. But here we're just counting all of the null values in our field. So all of our columns, we had red blood cells all the way to blood pressure, and it's actually counting out how many nulls. So we have, for our patients, 152 rows don't have a value for the red blood cells, and 88 rows or patients don't have a value for potassium. So we'd want to make sure that we're going through this data to see if that's accurate. Like, should this patient not have a value for red blood cells? Probably not. They probably should have some type of value. So we have to figure out how we want to handle this data. Are these patients that we ultimately drop from our data set? Can we find that data elsewhere? Can we impute it so it does have a value? All things that you need to look at, especially when you're exploring and preparing your data for modeling. Because this is the governing principle. Garbage in equals garbage out. I've said it before and will probably say it again, because the quality of information coming out can only be as good as the quality of information that went in, because the ceiling of your model is only going to be as good as that data going in. So in the upcoming slides and over the next couple of seminars, we'll talk about some ways to clean up your data, but it's going to be very dependent on initially what your data looks like, how it was collected, how it's been standardized, and how it's been stored. And using domain knowledge to adjust the data set and use it properly for the chosen model in question is the definition of feature engineering. So this is very popular in data science. Essentially, you are defining or manipulating the columns of your data to prepare it for downstream processes like machine learning pipelines or advanced visualizations. We want to make sure that it is guided by domain knowledge to make sure that we're addressing the data set properly, but there's a bunch of techniques that you can use within this feature engineer definition to alter your data, to add new data to it, or to handle it and prepare it in a certain way so that it is ready for modeling. Things like imputation, where you are filling in values, or are you handling outliers, keying in on them or dropping them? Are you binning certain features of your data set into specific categories? Are you scaling your data? So you're taking, 0 to 1 million and you are applying like a log transformation and applying like transforming that column to 0 and 1. Feature splitting, extracting date, grouping operations, these are all things that can be applied. Essentially, you're adding more information to your data set so that is ready for modeling. Just pause to see if there's any questions in chat. Don't see any yet, but feel free to add any questions as they come up as we can move on to modeling. So in our modeling step, we have now prepared our data. So this means that we have make sure it's ready for modeling and it's very clean and standardized. And then we can move into what our model is and our selected model. So a model is a representation of a real-world process. It uses simplifying assumptions to make problems more traceable. And the goal is to balance representing the real world to a high fidelity with a level of simplification imposed. So I'll touch on a little bit more about what that means. Essentially, it learns patterns from your historical data set. ML models use discovered patterns to make predictions or decisions without being explicitly programmed for a specific task. So you can think of it as baking. The computer's goal is to determine the best way to mix the data together to achieve a desired outcome. And that will all be done, on your computer with your chosen machine learning model without much, human input. There's two main types of machine learning. And after we finish the data science process, we'll go into it a bit more. But we have supervised and unsupervised. And the main distinction here is if you have labels and you choose to use them. So for our case, we have labels. Does this patient have a chronic kidney disease? And so that would be a supervised machine learning problem. More so, it would be a classification problem because we are trying to classify if this patient, yes, does have kidney disease or no, does not. It's a binary. Or regression, you're predicting a quantity. The temperature outside, the salary of a person, what their glucose level is at, that would be a regression quantity. Unsupervised is different where you don't have labels or you're choosing not to use them, and your machine learning algorithm will find those hidden groupings or patterns within your data set that may not be apparent to you just looking at the data by yourself. So it's going to use all of the features present and try to cluster it or group it together to figure out what those hidden patterns could mean. So first, we'll touch on supervised machine learning. You can think of it as a group of images. Say we have images of cats. We have the label that represents cats. Our machine learning algorithm is going to figure out what makes a cat a cat. Is it by color, features of the eyes? Is it if they have ears present? So then when you apply it in the real world, say we have our trained machine learning model that's used to identify if something's a cat or not, we can throw in new images it's never seen before, and then it can use that trained machine learning model to pick up on those same features that it's been trained on. So, okay, yes, this image looks very similar to what I've been trained on, so therefore it is a cat. It follows the same features of color, of patterns, of whiskers, of ears. And these images don't look like cats to me, so I'm going to label them as not cats. So I end up with a classification of yes or no. So regression is the task of predicting a continuous numerical variable. So here, for this example, using our same data set, we have predicting packed cell volume using hemoglobin measurements. You could also predict a quantity like price using square footage, or forecasting the price of a stock. So here, predicting packed cell volume using hemoglobin measurements would actually be a very successful machine learning model because it is such a linear relationship here. And when we're drawing our line of best fit using linear regression, you can get a very good predicted value using hemoglobin as a feature. And we'll touch on this a bit more in our next section. And then we have classification. So you are predicting if a class of something, do they have chronic kidney disease or do they not? Or labeling emails as spam or do they not? The same methodologies apply from regression to classification. It's just ultimately what label you want to predict. And then unsupervised learning, this is where we are not using labels. So instead, we're just going to feed in all of our images to our unsupervised machine learning algorithm. And our machine learning algorithm is going to figure out what patterns should we pick up on. And in this case, maybe it's picked up on both color and type because it's sorted it into two similar groups, this group here and then this group here. And now, as data scientists, we have to uncover what it's grouping it by. It's not going to give us a clear output of labels, unfortunately, that show us, here's what I grouped by color and by species, because that's clearly what it's grouping it by. Instead, we have to actually research what is similar about group 1 and what is similar about group 2 by ourselves. We start to become investigators. Dimensionality is a subset of unsupervised learning. This is very popular because it is the process of reducing the number of features in a data set while retaining as much important information as possible. So oftentimes, like our data set, we have a ton of dimensions, but as humans, we can only visualize, in 3 dimensions max. So you can't always visualize how those features are interacting with each other all at one time. Dimensionality reduction applies an algorithm to reduce those dimensions into, say, 2 different dimensions or principal components. So you can now visualize the same information about your data, but just projected onto a smaller scale or a 2D or a 1D visualization. That works hand in hand with clustering. So clustering is the process of partitioning your data set into different groups or clusters. Like we mentioned before, we want the groups to be homogeneous and the clusters to be heterogeneous. So you want the clusters to look very similar to one another, and you want the other clusters to be very different from, cluster 1 to cluster 2. You want those to be different, but within cluster 2, you want everything to look the same. And it's not always going to classify it as you would maybe want it to. It can classify things, based on color in this instance, or cluster it in by shape. So you have to uncover those hidden patterns of how it's grouping. And then finally, we'll move into data visualization. So visualizations can express aspects of the data that numbers cannot demonstrate. So they really tell the entire story about your data. This is important. You've spent a lot of time working on your data, understanding about it. And so now when you're presenting it to outside stakeholders or to users, you really need to paint that picture of what this looks like. An example we like to show is the Anscombe's quartet. On the right-hand side, we have 4 different data sets, and they all have the same descriptive statistics, mean, variance, and correlation. So if we were just to look at the descriptive statistics, because after all, data science is based on math, so let's just show the math, we would assume maybe that since they have the same mean, variance, and correlation, they have the same life cycle of the data. They're basically the same, right? But when we show it in conjunction with a visualization, the 4 bottom graphs here, we can see that they have a very different life cycle of data. We have a linear relationship, a parabolic relationship, a nonlinear relationship, and a nonlinear relation or a linear relationship with an outlier. So now when I see this visualization, I'm thinking way different than what I was when I just looked at this descriptive statistics. So it's helpful to partner them in conjunction. There is a lot of open source tools, things like Python, which we showed you snippets of, JavaScript or R, that all have built-in functionality to actually use or show visualizations within your notebooks. But there's also premium tools to achieve this as well. A popular tool that a lot of companies have is interactive dashboards, things like Tableau, Power BI, or Click, and many more. And these are helpful because you can actually show mini graphs all at one time on a dashboard, and you can actually interact with your data and see how those graphics change if one feature is selected. So it really gives your users or yourself kind of an entire picture of what's happening with your data, including your machine learning model predictions, all in one glance. And then finally, taking action. So we want to make sure that we are deploying the model and that we are maintaining it. One thing we can use to maintain our model is through different accuracy metrics. So if you have classification, you would have a set of accuracy metrics like accuracy or precision and recall, where you're measuring how accurate or precise your model is at predicting a specific class. If you are deploying a regression machine learning model, you may care more about mean absolute error, mean squared error, root mean squared error, R-squared score. This essentially is telling you how good your line of best fit is on your algorithm. It's important to maintain your model. It's oftentimes that data changes, it's inevitable. And so your model may not be as great at predicting if your patient has chronic kidney disease as it was when you deployed it a year later. So we want to make sure that you're tracking the model performance over a period of time to indicate when you need to retrain your model. Okay, let me see if there's any questions here. And then I'll move to our machine learning deep dive. So here we're just going to go over fairly quickly because we already have touched on supervised and unsupervised, but we want to take you into kind of the four core components of what's happening. So first is linear regression. And in linear regression, it's defined by two parameters. So y equals mx plus b. You may have heard that equation before in algebra. So it's the slope of the line and the height of the line. And the same equation applies to linear regression when you're deploying a machine learning model. You have two different parameters that your model is continuously updating and finding to find that slope of the line and that height of the line in order to create a line of best fit. So geometry, the first parameter is associated with this height of the line. The second is where it crosses the y-axis. And learning is just when your model is updating these parameters, your theta naught and your theta 1, and figuring out what is the line of best fit for your equation. So back to our original example of packed cell volume and hemoglobin, we could draw a line of best fit that looks good to us, using Excel or something, but you can also deploy a machine learning model, especially if you have multiple linear regression and you're using many features to predict a target variable. But your model is consistently updating to minimize the cost function or the least squares estimation. Let me see if this plays. Essentially, this is what is happening when your model is training. If it will start moving here in a bit. So this is called gradient descent. Essentially, when your model is updating or learning about your data, it is trying to find the least squares error or minimize the error severity. So it's going to update this parameter, and as it's updating, it's trying to find, the global or the local minimums on our chart. So it will continue updating, figuring out that error, and then, so it's going to draw a line of best fit, and then it's going to re-update its parameters to see if it can reduce that least squares errors function and update again. So it's going to update to see if the least squares errors is lower. It will be, and then it's going to continue training. So it's going to train over multiple iterations, hundreds or thousands of iterations, depending on how complex your model is, and then give you a trained model. You can also apply this to multiple linear regression, which is probably more common because more often than not, you may be saying, what is my hemoglobin, red blood cell count, my blood pressure, and many other features in order to predict, what is my packed cell volume. You can also do that through multiple linear regression. Gradient descent looks very similar, but instead it's a planar field instead of a two-axis or two-dimensional. Linear regression is useful because it's very simple. We can all understand that equation, right? Like the height of the line and the slope of the line. So it's easy to interpret and also give out, interpretability metrics to stakeholders, and it's computationally inexpensive. If I have a regression problem, I always start with linear regression first because you can train it so quickly. But cons is it oversimplifies many real-world problems because it does assume a linear relationship. And oftentimes our data does not act in a linear fashion. There are a lot of nonlinear components. So linear regression may not be the best fitting model where it will give you, the best R-squared score, but it's a good one to try at first. And it is sensitive to outliers. If we look at logistic regression, so we can jump from our linear prediction, predicting the packed cell volume, and now we want to predict logistic or a class of something. So if a patient has this chronic kidney disease, if you remember, that was our problem statement. So now our data is going to look very different. Instead of this graph here, where it's continuous value, we are going to predict if a patient has a chronic kidney disease. It's a yes or no. So our data is going to look very different, where we can't just draw a line of best fit here because that line is not doing well. We're going to get a high error rate because our predicted values are along this red line, and our actual values are these blue dots here. So our error rate is actually going to be very strong when we calculate our predicted versus our actuals. So here is where logistic regression comes in handy when you have a classification problem. It uses a sigmoid function, but essentially it looks like this, and there's a threshold set. So if anything is above a certain threshold, it will round up to the nearest class or round down to the nearest class. So you'll have yes versus no. So you will have a binary output. Yes, this patient does have kidney disease, or no, they do not. So logistic regression is a statistical method for analyzing, and it is binary, but you can also deploy non-binary predictions. So things like, is this a dog, cat, horse, fish, bird, like multiple classes? You can deploy a classification problem for that as well. In summary, logistic regression is easy to interpret, quick to train, and provides probabilities as outputs. So as linear regression is kind of your baseline model for regression problems, logistic is a great baseline for classification problems because it is very quick to train. But the cons, it has poor performance in large feature spaces, it can't handle large amounts of categorical variables, and it's best in binary classification problems. For both logistic and linear, or should I say classification and regression, there is hundreds of models to choose from in the machine learning world to accomplish your task at hand. So these are like the baseline, and all of the other models are kind of built off of or are subsets of these two big ones. But you can get much more complex to fit the data that you need. And then we turn to unsupervised. So this essentially is what we're hoping to do in our unsupervised paradigm. So we are taking in raw data that's been pre-processed, of course. It's been formatted, cleaned, and prepped for our algorithm. We're going to apply a different algorithm, an unsupervised learning algorithm to it, and we're going to ask it to find our clusters. Then, as data scientists, we review and look at those clusters to find what patterns can be uncovered. So for instance, you have a microscope slide, and you want to classify the images within the slide. So you have, a couple of different components of different, maybe like blood cell components, and you want to apply an unsupervised machine learning algorithm to group these. And it's grouped it into 3 individual classes. Now, upon closer inspection, you can identify these classes as their components of what they are, DNA or red blood cells. And you now have 3 individual classes that you then uncover. It doesn't always group it as nice as this. Of course, this is like very clearly grouped in individual things that we would hope it to be grouped in, but you're not necessarily in charge of exactly how it groups things. So dimensionality reduction, this is when we reduce our dimensions. You have a high feature space, something like what is this, like definitely over 10 features, over 20 maybe. You have age all the way to if they have chronic kidney disease. If we wanted to see how all of these features interacted with each other, we would need 22 different dimensions to see that. So instead, we can apply principal component analysis. Now, principal component analysis is an algorithm that you apply to your data set, and instead of 22 dimensions, we reduce it into 2 principal components. So it's a great way to feature or to visualize feature-rich data. And we can actually already see, just by applying principal component analysis and reducing our dimensions, we can actually see groupings starting to form on our data. So maybe we look at and identify if these specific groupings after applying PCA mean something. Maybe that group in blue, all of those patients don't have kidney disease. Maybe that's a hypothesis we could state, and we look to uncover more. And maybe this grouping, they do have kidney disease, and they're kind of grouped all in like a larger scale cluster. We don't necessarily know if those are the labels, but we can apply k-means clustering to look at that. So k-means clustering, or clustering in general, is a common algorithm used in conjunction with PCA, but it actually describes the process of grouping data into shared characteristics. They may vary by data, and it takes a sample as an input and outputs the cluster that it belongs to. So this is an iterative process of finding groups of data. So we actually apply a new algorithm called k-means, and it iterates until it reaches the best solution of clusters in our problem space. So on the left-hand side, we have our original unclustered data, and then by applying k-means, we've actually colored the data into specific groupings. And then we have 3 groups here. We have a green, a blue, and a red, and we can start to uncover characteristics about these features within these groupings. So if we go back to our problem statement, we can apply clustering or k-means to our principal component output. So on the left-hand side, maybe that was our prediction of maybe everything once PCAs have been applied, it's in this clear group here. Maybe they don't have kidney disease. And in the left-hand side, they all have kidney disease, or they all have kidney disease. So we have 2 individual groups. So now once we apply our clusters, we can color our cluster by category. So for our hypothesis, we stated, one has kidney disease and one doesn't. We've actually colored this, so everything in yellow does have kidney disease, and everything in purple, I believe, does not have kidney disease. And we can see that these colorings are very much overlapping. So it's not actually identifying what has kidney disease versus what does not. It's clustering it by different features within that data set. And upon greater investigation, we would be able to tell you maybe what it's clustering it by, different features apart from our target variable, because of course we didn't apply our target variable to our unsupervised learning algorithm. Okay, in summary for k-means, it is easy to interpret and implement. It's computationally inexpensive, and it guarantees convergence. The results are it's highly variable and dependent on initial values. It's sensitive to outliers because it's unable to group outliers into clusters, and it struggles with data of varying sizes and densities. So what we have left is a stretch break, and then we're going to take you through our deep learning overview and then our specific topics, computer vision, time series, and natural language processing. So I'm going to set you guys on a 5-minute break now. So we'll come back at the 12. I'm on Central Time Zone, so mine's 1:12. Okay, now it's 1:14. And then if you have any questions in the meantime, feel free to come off mute and ask me or put them in the chat. But I will see you guys back in 5 minutes. Sorry, I see a hand up. I don't know if, okay, never mind. Maybe the person's hand's down. And I actually don't know if you're able to come off mute. There might be a setting that you're not able to come off mute. I'm not too sure. So your best bet may be putting things in the chat if you have the chance to write it out.
You can put anything in the chat. Chat is inactivated.
Okay. Oh, that you can't put anything in the chat?
Yeah.
Interesting. Okay. What about, do you have the Q&A, the Q&A little toggle at the top? You can also come off mute.
Yeah. No, it says not available for this event.
Okay, okay.
The Q&A is not available, but the chat should be enabled.
Okay. But if you have a question too, feel free to come off mute at this time and ask it.
Yeah, thank you. Actually, it's a great overview. I have a few questions, maybe a very simple one. With all AI now capable of processing the unstructured and non-standardized data, do we still need data standards?
For non-structured data?
Yeah, any unstructured, unstandardized, non-standardized or unstructured data, a lot of them there. We are focusing on standardizing the data now because AI is capable of, kind of getting the data, even if it is from the non-standardized format or unstructured. Do we still need to, sweat too much on the standardizing the data or focusing standardizing the data?
Yeah, and it might look a little bit, so if you have unstructured data, still to standardize it, yes. It may look a little bit different. So maybe you care more about your entire data set and making sure that it's processed in the same way. So each image is processed in the same way and ultimately, stored in the same way so that you can pull from that historical data. It may look a little bit different in collecting the data we would love, standardized data practices to be implemented whenever data has been collected and start moving towards that. But if it's unstructured, it's going to be harder to, format that in a different way. For images, of course, like looking at the same thing every time. For audio files, it is at the same sound or level. So there's different things to, I think about, but having it standardized. So when you pull in your historical data set, it looks very similar or as similar as it can look, is important for both structured and unstructured.
Thank you. I have a very quick question now. So you touch on the dimension reduction, right? Before you cluster your dimension reduction, how advanced is our capabilities on the dimension reduction now? Can we reduce the thousands of dimensions to significantly lower now?
Yes, you can. We have great technology there. I will say it's more, I would say, computationally expensive PCA in general as a solution to reduce those dimensions. And sometimes if you have, thousands of dimensions, reducing into 2 principal components or 3 principal components can be a bit difficult, but we definitely have the technology to do that today.
Thank you.
Yeah. Any other questions?
Yeah, I do have a question, if you allow me.
Yeah.
Yeah. Thank you for the presentation. It's amazing. I have a question regarding to the modeling. How it's important to use the modeling, like when I have the data to conduct the analysis. So, is it like how it's critical steps? Is it like important to do it, and what's important of it?
Yeah. So you don't necessarily need a modeling solution for every problem statement, because maybe your problem statement is not, let's predict this end value. I know a lot of, projects end at like maybe some high level of data analytics, and maybe you take all of your prepared data, put it into a dashboard so you can uncover trends or patterns yourself, and you don't necessarily need a prediction. So modeling is not, I would say, important for all problem statements. Going back to that, like, you don't need to engineer a data science solution if data science is not needed. I think it's definitely important to keep in mind. But if you have a prediction of something that you want to create, trying to go back to it, then modeling can be very powerful and very useful to help you even put the human in the loop. So maybe you're giving a prediction to help out a person, and they can take that prediction as like a starting point for something. So that prediction maybe doesn't end in actually taking action from that prediction of the machine learning model alone. Maybe instead it's given to a researcher or doctor, so then they can take that as their starting point and then make their own prediction or their own evaluation or prescription from something.
Okay, great. Thank you so much.
Yeah.
Another thing, I don't know if you like have a printout or you send this presentation to the emails, because I see it's like it's good resources to start with for me.
Yeah, I don't have an issue. I can definitely send this. I believe I can send it to Anya, and if you wanted to send that out afterwards, is that possible?
Yeah, all this presentation is going to be recorded, and we'll also publish the materials onto the Central Repository website. So yes, this will all be available.
Great. Thank you so much, guys. Thank you.
Yeah, thank you. Okay, then without further ado, I'll pass it to my coworker, Gordon.
Awesome. Yeah, thank you so much, Erica. That's a wonderful, wonderful overview of the data science process. Give me 1 second. I'm going to share my screen here. And if you could confirm, Erica, can you see that?
Yes, I can.
Sometimes it takes a couple tries. Okay, awesome. Yeah. Well, thank you so much. Yeah, that was a wonderful overview. Thank you, everybody, for the questions during the break. We really do enjoy engaging with all of you. If you do have questions during the remainder of the presentation, please drop those in the chat. Erica will be on standby to answer those in real time. If I see something sort of out of the corner of my eye, I'll try and address it as well. And then, of course, at the end of the presentation here, we'll have another question and answer session where you guys can come off mute and we can discuss things further. So it was a great question that was asked during the break about, do we always have to use modeling? And as Erica mentioned, the answer to that is no, you don't always have to use modeling. But in the cases where you do have to use modeling, what we wanted to give you is a preview of some of the things that are good to have as like a basic, toolkit to start from. And then we also want to give you a little taste of some of the things you might be hearing about in the news, some of the things that you might be hearing about, your boss saying, hey, can we do AI? Can we leverage this type of technology to our advantage. So we want to give you just a very, very basic taste of something called deep learning. So deep learning is an approach. It's a particular approach to artificial intelligence and machine learning. And so the way you want to think of the diagram that you're seeing here, Erica talked to us about artificial intelligence is about creating systems, particularly computer systems, that can mimic human intelligence in some way. So a long time ago, that was just doing basic arithmetic, right? Now we have models like ChatGPT that can basically do anything you want, right? They can generate images, they can, write you a resume. ChatGPT models have also been shown to pass, high-level examinations like, the LSAT, PhD level qualification exams, MCATs, all that kind of stuff. So artificial intelligence has grown quite a lot, of course, especially recently. And so the way you're looking at this diagram is you say, okay, well, how do we design systems to be intelligent? And so each time you're sort of drilling down in this diagram, you're answering the question, how? Now, a calculator doesn't rely on what's called machine learning. By machine learning, we mean the capability of the system to update the way it behaves as new data is introduced to it on its own. So when you type in your calculator 3 + 1, right, that's not changing the way the calculator behaves. It's not updating any internal system on its own just because you typed in 3 + 1. Whereas machine learning, as you feed new data into the system, it has the capability of updating itself, from learning from that data, discovering new patterns and trends. In a nutshell, you want to think about machine learning as akin to pattern recognition. That is essentially that's an oversimplification for sure, but our level of discussion here today, that certainly serves our purpose. So we have pattern recognition tools essentially when we talk about machine learning. And then deep learning, so as we drill down into this diagram, you're asking another question, how? So how do we pick up on patterns in data? Many, many different ways of doing that. Deep learning is certainly in vogue right now. It relies on something called neural networks, and that's what we're going to discuss next. So deep learning relies on neural networks. It gets the name because these things are modeled after the human brain. Okay, so deep learning is very popular these days because they outperform older machine learning algorithms on a number of tasks, particularly particularly those that include larger and larger volumes of data. So Erica mentioned things like the Amazon recommendation system, things like ChatGPT, where these companies, Amazon and OpenAI and Microsoft and companies like that are able to collect very, very large volumes of information. They're able to process those large volumes of information and discover patterns that any normal human being wouldn't be able to do on their own. So the reason why this is so hot is because we have abilities to store and collect large volumes of information in unprecedented ways, and we're able to analyze and look for patterns in that data using computers that are getting faster and faster and faster every day. So as I mentioned, deep learning is inspired from biology. And this actually follows an engineering principle that is common across many different disciplines. It's what's known as biomimicry. So if you have a problem you need to solve, but you don't know where to start as an engineer, maybe you look to nature to get some inspiration as to what it is you want to do. So I want to design something that's aerodynamic, right? I want to create something that flies really well or cuts through the water really well. So maybe I look at a dolphin, for example, if I want to design a submarine. Or maybe I look at some sort of bird of prey, like a falcon or a hawk, if I'm designing an aircraft, right? We look to nature to inspire us and what we can sort of biomimic in our engineering designs. And the same is true when we're talking about detecting patterns in data. Now, I say this as humbly as a person of the human race can say this. Maybe this isn't the case, but to the best of our knowledge, the best pattern recognition device in the world or in the universe, as far as we know, is the human mind. And so it inspires you to say, can I digitally sort of mimic the way the human brain is set up? I am not a neuroscientist. I'm not a neurobiologist by any means, but hopefully we can see at least the basic idea that is being alluded to here. So on the top, you have an actual neuron, right? You have a cell body that has a nucleus. Essentially, that thing takes in, biochemical signals, electrochemical signals, processes that input in some way, and then shares that processed information with other cells in the network, i.e. your brain. The exact same thing is happening when we're talking about a deep learning neural network, right? Now, the difference here is that your computer and your brain do not function, they do not process the exact same type of data. Whereas your brain is relying essentially on electrochemistry, computers only understand one thing. Computers only understand numbers. And so the type of information that has to flow into a node in the network has to be some type of numeric value. That numeric value is processed using mathematical formulas and equations. And then once that data is processed mathematically, the output is then shared. The output calculation results are then shared with other nodes in the network. So there's a slight difference in the type of information that's being processed, but the way the information is processed and how it is shared in the network, that is a similar feature there. Okay. This looks like a very complicated slide. I'm not going to dwell on it too much. It's essentially emphasizing what I just spoke about. So the type of data that flows into a network, labeled in blue here, these are all numeric values. Those numeric values are then weighted in terms of their importance. So some math takes place, some multiplication takes place, and then more math takes place. It's all just math, okay? And I'm trivializing that to quite a degree, especially for someone that has a math background. But essentially, you're doing multiplication and applying some very specially chosen functions to get this pattern recognition software to work. That's again, don't lose the forest for the trees. So there's some complicated math, but picking up on the patterns is what this is all designed to do. And the reason that this has become so popular lately, and AI and things like that have really exploded in the last 8-ish years or so, is because Google put out in 2017 a paper called Attention is All You Need. And essentially what they discovered is if you set these neural networks up in a very particular way, these neural networks can be good at modeling human language, so the ChatGPTs of the world. These things can be very good at computer vision tasks, which is what we're going to see in a little bit. They can be good at detecting and creating video, right? Generating audio files. Essentially most of the generative things that we as human beings can do. This special approach to neural networks is very popular and has become very, very powerful. So there has been a boom primarily based on that paper. And so again, you're just seeing here the basic structure that exists within a neural network. So on the left-hand side, you have some type of input data. right? That data is going to be a collection of numbers, whether that is numeric data associated with, say, the kidney disease data set that we had before, or maybe that's a collection of numbers corresponding to pixel values from an image, which we're going to see in just a little bit for a computer vision task. Some type of numbers. And then at the end of this diagram is where your output is made. So some type of prediction, some type of calculation, final calculation is made by the model. And any type of math or processing that happens between the input data and the final output prediction, those are referred to as hidden layers, hidden processing layers. And so the more hidden layers you have, the more nodes you have in your network, right? The more of these circles, these mathematical processing nodes that you have in your network, generally the smarter, if you can use that word, the smarter your model is going to be. So the ChatGPTs of the world have on the order of billions and trillions of these mathematical processing nodes associated with them. The model Erica showed us, the linear regression model, if you can actually write that as a neural network, that actually will just have a simple input. It's going to have 2 nodes in it. So the simple neural network is not very smart because it only has 2 nodes, whereas, again, ChatGPT and things like that are going to have billions or even trillions of these things. And it's all about getting the math and the numbers just right. And that is what these artificial intelligence and machine learning algorithms are trained to do. Configure yourself in such a way that you pick up on the patterns in the best way possible. There are lots of different tools out there for building out neural networks. We've demonstrated to you a couple of just Python code snippets. This isn't a Python course, but we wanted to show you, like, Python is about as user-friendly as a programming language can be. And generally, it doesn't take a lot of code to produce something of really high value. A lot of the things Erica was showing us were 1, maybe 2, 3 lines of code at the absolute most. There's definitely a learning curve, but it's not too bad relative to some of the other programming languages out there. As a matter of fact, if you were interested in creating your own neural network, right? So you decide that, hey, linear regression isn't for me on this problem. Principal component analysis isn't for me on this problem. I want something that's a little more flexible. Can I use a neural network? And Python supports things like TensorFlow, things like PyTorch that allow you to create your own neural networks, believe it or not. And there are many open source repositories out there. A popular one is called Hugging Face, where you can go and actually download neural network models that other people have trained, so you don't have to do this from scratch. Now, I haven't looked on Hugging Face recently to see if there is something specific to diabetes and kidney modeling, but I guarantee you there are things in the medical space, and it would not shock me in the least to find something on there where someone's trained a neural network to look for patterns in, again, diabetes and kidney disease data. Okay, so some of the pros around neural networks, they are able to capture much more complex, much more nonlinear relationships in data. Typically, they do better with larger data sets, which is what most agencies and organizations are doing, collecting large volumes of data. However, the more parameters, the more complicated and deep your network is, right? The more nodes, neurons you have in this network, the harder it's going to be to train these things. This is why you see in the news companies like OpenAI and Microsoft pouring billions of dollars into this industry, because it takes a lot of effort to train these models. It takes a lot of effort to power these models. Microsoft was even rumored to be buying 3 Mile Island last year to restart the nuclear reactors there, because that's how much power they need to work with these things. Lots of data is needed, and then it's very difficult to explain why a particular input leads to a particular output. So there's a very black box nature to these models. Okay, so we're going to dive a little bit deeper here into some of the specific artificial intelligence, deep learning neural network applications that you might hear about, that you might come across. We want to give you a little bit better understanding there. And we'll talk about this at the end, but we also have an artificial intelligence fundamentals course that you might be interested in. This is sort of leading into that. So the 3 types of specialized models that we're going to talk about here: computer vision. So essentially, can we train computers to look at images, to look at video, and understand them at the same or better level as a human being? It's particularly not just any human being, but a specialist, a specialized analyst in a particular field whose job it is to be good at detecting certain things in an image. So if you need a concrete example, think about a radiologist, right? A radiologist is looking at things like MRIs and X-rays. they're supposed to be very good at picking up on different, maladies and diseases and types of cell abnormalities and things like that. So can we train a computer vision model to be as good, if not better, than a highly specialized radiologist, for example? Time series analysis is about predicting the next element of data that exists in a period of time. And then natural language processing, we've touched on that just a little bit. We'll see some examples. Essentially, what we're trying to do here is get computers to be as good, if not better, at human beings and understanding natural language. So meaning things like text, written language, as well as speech. This is not going to be limited to just the English language. Natural language processing techniques and natural language processing models exist for pretty much every language out there. The degree to which they have been developed, of course, is going to vary quite a bit. English is certainly at the top of that list, but just know that this conversation we're going to have on NLP is not limited to English, even though that's the language that we're using here today. So computer vision. Okay, again, this is all about getting machines to understand and recognize patterns in visual data as good as, if not better than a human being. So I mentioned to you before that your computer only understands numbers. So you might ask the question, well, if my computer only understands numbers, how in the world do we go about getting a computer to learn from image data, for example? So essentially what the computer does is it goes through and it scans and it looks at each individual pixel that exists within an image. So a pixel is like the atomic elements, if you will, of any image. Your computer screen right now, what you're seeing right now is, of course, not me in the flesh. What you're seeing are billions of dots, little dots that are little lights that are lit up right now. That's a pixel. That's what a pixel is. And depending on how bright the pixel is and depending on what color the pixel is, those values are actually associated with numeric quantities. So your computer is actually seeing those numeric quantities, and through those numbers is able to scan through each of them and detect patterns. Things like differences in shading, things like differences in texture. So for example, we see there's definitely going to be a texture difference between the cat's fur and the tree branch, for example. There's going to be a difference in texture between, say, the grass and the water in the background, right? So there are different algorithms whose job it is to pick up on these different features, right? Different sort of angular shapes, for example, the shape of the cat's ear, much more angular than, say, the shape of the cat's, back or something like that. So there are components, right? The computer is able to look at and detect each type of those things that we as human beings just very naturally do. Changes in color gradient, changes in shading, right? We can see that the light here is a little bit lighter on the cat's right shoulder as opposed to, say, the cat's chest. Right? The computer is able to look in that pattern of numbers, those pixel values, and determine those changes and differences. So that's how computers are looking at images, essentially, by looking at those patterns in the pixel values. So what is it that we expect computers to be able to do once they're looking at these images? So as with everything, there's all kinds of nuance and, you can drill down a lot farther. But for a basic course, a basic introduction, there are three main types of computer vision tasks. So what you want to be able to do is object detection. So be able to can you even determine that there's something that you should be focused in on? So there's lots going on, even in a simple image like this, right? We've got the animals, right? The puppy, the two kittens, the rubber duck. We've got the bucket, we've got the grass, we've got the flowers. It looks like maybe a brick wall in the background. Can you, the computer, detect what's sort of most important? What should your eye, for lack of a better word, be drawn to? What would a human being's eye be drawn to, right? And we could debate this all day long, but I think most people would agree, the eyes for the average person, it's going to be drawn to the four things that have boxes around them right now: the puppy, the two kittens, and the rubber duck. That's sort of what is going to take the main focus. So can we get a computer to detect what is of most relevance here and sort of ignore the rest? So that's kind of step number one. Step number two, okay, great. You've identified the things that are important, but now you need to be able to tell where one object ends and another begins. And that's what instance segmentation is. Can you determine where the end of the dog is and where the beginning of the kitten is, or where one kitten ends and the other begins? That's what we mean by instance segmentation. And then lastly, can you classify? Can you actually put a label on what it is you've detected and segmented out? So for example, right, labeling the things that are in red as cats, labeling the thing in blue as a dog, and labeling the thing in green as a duck. These are the three primary, motivators for working on computer vision tasks. So computer vision, one of the first computer vision tasks was actually to design something that could detect human handwritten digits. This is referred to as the MNIST data set. I can't remember exactly what that acronym stands for off the top of my head, but essentially what the model was trained to do was to look at collections of handwritten numbers. So you see we've got, I don't know, 10 or 15 rows of handwritten single-digit numbers. And can the model go through and look at the pixel values and decide, okay, this is a 0, or this is a 7, this is an 8. And this is obviously a very challenging problem, because this is the type of unstructured data that Erica was talking to us about before, right? Now, to store just a single computer value of 6 in a spreadsheet is very normal, or the number 9 in a spreadsheet is normal. What you can't typically store in a spreadsheet is the handwritten data itself, that actual image. And there's going to be a lot of variation, of course, in people's handwriting and things like that. There's even cultural differences between the way people draw 7s. So for example, I used to draw 7 like the first few rows here. And I had a student from, I believe it was Africa, say, she would prefer if I actually drew my 7 with a dash through it. And for the last 15 years, I've been drawing 7s with a dash through it because, someone said it was more clear for them. So there isn't a standard way that people do things, and this makes it really, really hard. Computers like rules. Computers like predictability. They like going through a set sequence of steps. And so any sort of deviation is something that has to be engineered and overcome. And that's sort of one of the miraculous capabilities of these neural networks, is that they're able to sort of pick up on all these different kinds of things. I have just a little bit of time, so I wasn't sure exactly how much time, but this is a fun thing to play around with. I'm going to drop it in the chat. I'm going to demo it here just live, but just to give you a sense for how, where did my chat feature go? Here it is. Just to give you a sense of what computer vision is all about with regards to the MNIST data set. So here, someone has actually designed a website where you can play around with the MNIST classifier, right, with predicting single-digit numbers that are drawn by a human hand. So on the left-hand side, there's this sort of scratch pad here, and you're able to draw a handwritten digit and see what the computer is picking up on and what type of prediction it's making. And so the first layer, we talked about layers in a neural network. So the first layer is the input. And you can actually see the pixelated values, the little atomic elements, the little squares that the image itself is broken up into. At the end is the output layer, so the final prediction. It's shown here as well. The final guess is 3. And then we have these intermediate processing layers, which, as I mentioned in a computer vision task, it's their job to pick up on different important elements in an image. So for example, the first component of the first layer looks like it's picking up on, say, horizontal components that are part of the handwritten image. The third layer, for example, the second is maybe picking up on more like curved or arced components. The third looks like it's picking up on more like corners maybe, right? The fourth or fifth looks like it's picking up on more vertical pieces. And once these patterns are detected, right, a lot more processing has to happen, of course, but even as first initial pass, we can kind of see what the computer's up to and why it's determining why that first guess might be 3. Okay, so feel free to play around with that. But that's what computer vision and the MNIST data set is all about. And as I mentioned, right, so your computer only understands numbers. And so this slide is meant to sort of codify that idea a little bit more. All right, you might say, well, again, how does this happen? So when you're looking at me right now, there are actually just 3 types of lights that are, part of your computer. So there's a little red light, there's a little green light, and there's a little blue light, and there are billions of those. And so what you can do is essentially quantify just how red a pixel is, just how green a pixel is, and just how blue a pixel is. And by combining just those 3 colors, we can make over a million colors. So way more than is in the standard, Roy G. Biv rainbow, right? And this is how your computer is seeing images, typically, right? If you have a black and white image, then you're talking about grayscale. Again, there's always exceptions to the rule. But for our purposes, this is how the overwhelming majority of computer vision models are going to work when we're talking about a color image. Okay. And so here, just sort of putting on the slides what we just demonstrated in that applet that I showed you before. So here, right, if the computer has picked up on patterns, right, the computer is picking up on chunks. It's not seeing the whole image, right? Remember, the computer's seeing things one piece at a time. So maybe the computer picks up on sort of a round component and a vertical component, and it has to make a guess as to what the model output should be. What's most likely? And that's what computer vision models and all these models are working on. What is the most likely outcome, right? They're not perfect. What is most likely is going to depend on the type of data that they have been trained on, the type of patterns they've been taught to look for, which is why bias mitigation is so important, which is why representation in data is so important. Because you could have a model that is working really, really well, but if it's only trained on data with a very limited scope, it's going to miss the bigger picture. Okay, so here, this is likely to predict, say, like a 9, right? So there you see that. Maybe a 6 might also be something that would be a good guess there. Here, the computer may have picked up on 2 round loops, and so maybe the prediction here is an 8. Maybe a 0 would be something that's maybe not quite as likely, but possible. So there you have that there. And then here, maybe a little trickier here. So we've got 2 vertical components and a horizontal one, but this is probably likely going to predict a 4, which you're seeing there. Okay, so here, again, just these neural networks, the way that there's not one type of neural network. Depending on what it is you want to do, right? Depending on your application, there's going to be different types of neural networks out there for different applications. The types of neural networks that are set up for computer vision tasks, again, the transformer neural networks I referenced before, as well as what are called convolutional neural networks, right? So even if you don't remember all that, the only takeaway I want you to have is there's not just one type of deep learning network. There's not just one type of AI. There are many different types depending on the problem you want to solve. And the layers associated with the models have a job for picking up on specific patterns. And that's what's detailed here on this slide. And that's what we saw in the applet that we just played around with a moment ago. Wanted to give you an example of how this is being used in the kidney disease space. So I am not an expert in this space by any means, but look for some research here. So I took this from a Nature paper that I Googled. The link is there. Basically, what you're seeing here on the left are images of a human eye, right? Particular the retina. What you're seeing then is, right, remember that one of the main things in computer vision is about picking up on what a human being thinks is most important. So in column B, this is an expert, a doctor has gone through, likely an ophthalmologist or an optometrist has gone through and identified, right, which veins and things like that they're seeing, right? And then on the right, you're seeing what the computer picked up on, what the computer's object detection was and its segmentation was. And you can actually see that the computer does a really nice job mirroring what the human labels are. So this is an instance of object detection and segmentation looking at the retinal data, because retinal data, the way the health of your eyes is very closely related to renal function, for example. And that's actually what this paper is about. Okay. Computer vision is not perfect though, and so it can actually it might actually be surprising, the level to which like some problems are easier to solve than others, basically. So for example, right, this cartoon from XKCD is saying, the boss wants, when somebody takes a photo, they want this app to determine which national park that person is in or whether they're in a national park or not. And so the engineer says, oh, that's actually pretty easy, which you would think would be a relatively hard problem. And then the boss says, can we check whether the photo is of a bird? And then the engineer says, I'll need research team in 5 years, right? So it can actually be kind of shocking just how different the level of difficulty is. You might think that the national park thing would be harder than the bird thing, but yeah, it's just a cartoon, but it is nevertheless true. And another sort of fun example we like to throw in as to why computer vision is so hard sometimes is because for you and I, right, we pick up on visual cues very naturally, but a computer, right, like you can see, right, the Chihuahua versus the baked muffin, right? This would be a really hard thing. It's a very nuanced difference there because the blueberries look very much like the eyes and the nose. The coloring is very similar, right? We definitely have machine learning models that can make this distinction at this point, but this is just meant to illustrate just how difficult it would be, right, if you were a new AI engineer to try and determine, all right, how do I really differentiate these two things? Because they're very different. objects, obviously, but very similar in the way that they're structured. Okay. So time series analysis, this is when you want to predict a future numeric value based on previously known numeric values. Lots of different applications here, but stock market prices are sort of the garden variety example. So you might be able to pull in a whole bunch of different stock price data, and you want to know what the price is going to be tomorrow or 10 years from now or a month from now if you're interested in shorting or going long on stocks, that kind of thing. So time series is just collect data over time and then try and predict a numeric value into the future. When you're working with time series data, you have to be really careful to control for something called seasonality. So seasonality are natural trends and fluctuations that occur, periodic trends that exist within a data set. And so there are many different tests out there for testing for seasonality. There's something called the Dickey-Fuller test, which you see here is passing with flying colors, much lower than 0.05 level of threshold there. But essentially what's happening is, again, natural patterns that exist in the data. If you ever looked at, say, electrical consumption data, you would see that people tend to use more electricity, at least in North America, during the winter and the summer months, for example, and then consumption goes down typically in the fall and spring. That's just another example of time series with some seasonality to it. Stationarity is all about how much your data fluctuates over time. So essentially, does it have any, so we see there's seasonality here. There's definitely a pattern to the data. But when we talk about stationary, is that data sort of trending up? Is that data sort of trending down? Or is it sort of getting more oscillatory in nature? That's what we mean by stationarity. And controlling for stationarity is really important to getting more accurate predictions. If your time series model isn't stationary, you're much more likely to have something that doesn't make predictions really well into the future. Again, there's lots of different techniques out there for taking something that isn't stationary and getting it into a more stationary state. But you can see, right, if something is fairly consistent over time, right, just intuitively, it's going to be much easier to make a prediction about what happens in the future, as opposed to if things are sort of going haywire, right, if they're not stationary. And then the last thing we're going to talk about in time series are what are called smoothing methods. So a lot of times what you don't necessarily always need the like super high frequency of the data, right? So you might be measuring something every minute or every second, or if you're doing something really high end, every nanosecond or something like that. And a lot of times having that volume of data, it can actually disrupt sort of what the overall trend or pattern is in the data. So there are methods out there for sort of smoothing things out, for saying, okay, like what matters most is the overall trend in the data, not so much every single peak and valley, not so much every spike in the data. And typically dealing with data that has been averaged out or smoothed out a little bit, typically, not always, but typically lends itself to making better long-term predictions. So you can see here in the example, the blue values, this is the raw data. You can see lots of spikes, lots of jumps, very high volume of data, whereas the green is the smoothed out or averaged out data here. And while the green is not representative of like the true phenomenon, it still does capture to a very high degree the overall pattern and the overall behavior that exists within the data. Just like Erica talked to us about principal component analysis. When we reduce our dimensions down, right, we're definitely losing some information. But is that information loss something we're willing to give up, right? If we gain further insights and if we don't lose a high degree of fidelity with the representation of our data. And the same is true here of averaged out data. And there are many different methods for doing smoothing. The next two slides, I'm going to go through them quickly here. The math isn't super important for our purposes. Just know that there are many different ways of going about smoothing out your data, including things like exponential smoothing, which basically is saying, right, so it's great, maybe I've got data going back 50 years, right? But really, in most applications, not all, but most applications, typically the data from more recent should be given more weight than data from a long time ago. So an exponential smoothing method says, okay, I care about the data from the distant past a little bit, but not as much as I care about stuff that happened more recently. And it's able to sort of weight the data based on, how recently it was recorded. We also have ARIMA models, which are able to predict out in the future. Essentially what these do, they're able to take prior data, compute the smoothed out averages. So ARIMA stands for auto-regression, means you're relying on past information to predict future values. Integrated allows you to sort of look at differences that exist between the data points. This is helps you smooth out the data a little bit, as well as some of these moving average techniques that we talked about before. All of these are meant to make your predictions out in the future that much more robust. So if you're new to time series modeling, definitely look into ARIMA models. They're where most people should start their journey there. Okay, time series, right? This cartoon, like the other, just meant to be a little bit of a humorous take on what it's all about. So I finally found it, the scroll of truth, and then unfortunately, it's impossible to predict stock prices. So there's no way to know with any time series, but particularly those. All right, and our last submodule here for you is natural language processing. So just like computer vision data, this is unstructured. It doesn't sit naturally in a tabular format, basically a spreadsheet format. And so it can be very difficult, right? There's different meanings associated with, the exact same phrase, for example. So I'm a huge metal fan, right? Could be someone really enjoys, Metallica and Pantera, or, right, this may be the inner thoughts of an actual fan, right? So different meanings for the exact same sentence. How do you get a computer to understand context when it's already hard enough for human beings, for example? So for this, we use natural language processing techniques, right? Essentially what we're trying to do is try and get the computer to understand context, trying to get it to understand semantics and structure, the grammar of a particular language, for use in things like chatbots, for use in things like large language models, generative AI. Those are the common approaches to using natural language processing today. So just as a quick example, right, you might have an email, right? And so what are you looking for as a human being in an email? Well, I'm looking for who this is sent by, what the timestamp was, of course, the body of the email, right? Is this spam or not, right? And a machine learning algorithm is doing the exact same thing. It's looking at the sender, it's looking at the body, it's looking at the structure, the way the words are typed and spelled, and the grammar and all that kind of stuff, and making determinations on whether something like this is spam or not. Okay, and here, right? Not just spam, but also like, hey, maybe this person's trying to send you a calendar invite. Do you want me to set something up for you automatically? So NLP, right? The overwhelming majority of data is actually text data. I think most estimates are around 80% of the data generated on a daily basis is text data. So this is a huge area of information that we're only just starting, relatively speaking, to mine out and gain value from, especially when it comes to automating pipelines, being more efficient in day-to-day life, like this. So just like before, you might say, well, how does a computer, if a computer needs to understand numbers, how do we go about taking a piece of text and converting it to a collection of numbers? So if you have a body of text, say today was a great day, and I have another body of text that says something like I like puppies. One way to go about doing this is to take each unique word, sometimes you'll hear that referred to as a token, each unique word or token, and turn it into its own column. And then what you do is you count how often, with a frequency, that particular word appears across the documents. So row 1 is the row for document 1, and row 2 is the row for document 2. So for example, we see the word day appear in document 1 once and 0 times in document 2. So recorded there. Great appears twice in document 1 and 0 times in document 2, etc. So this is just one way of getting computers to understand human language by converting it to a collection of numbers. This is a very naive approach. It's a very basic approach, but it serves as the foundation for many other more nuanced and subtle approaches. Okay, so, and this is referred to as an embedding, but again, just sort of showing you the summary of what we talked about there. All right, now what's not super ideal about this very naive approach? Well, certain words in any language, but particularly the English language, tend to occur with more frequency. And a lot of times those words don't carry a lot of semantic meaning. So words like the definite article or indefinite article, of, right, if, but, and, right, those tend to appear with great frequency, but don't carry a lot of meaning. And so we need ways of diminishing those words' importance, right? Pure counting of words is not going to do the trick. And basically, there's some math that allows you to, there's a lot of techniques for removing, just straight up removing words like that from your data set to begin with. Those are called stop words, getting rid of those. And there's also different mathematical formulas that measure the information content. That's what the logarithm represents here, the information content that exists within a particular data set, or in this case, within a particular token within your data set. Okay. So there are more sophisticated ways of going about doing this than just some of these count embeddings and vectorizers. There's more complicated things. There's something called word to vec. This came out around the same time as that attention is all you need, just slightly later. And this was another sort of shift in just how good we were able to represent text data that allows computers to analyze it with greater and greater accuracy. So the way this essentially works is it converts your data into vectors, into arrows. And the great thing about vectors or arrows is it allows us to sort of intuitively see just how close two pieces of data are to one another. So when we have maybe sentences or documents that have the word king, man, queen, woman in them, right, by vectorizing them, we can see, right, which arrows are closest to one another. And this is how the computer is going to interpret whether two words are similar or not. So king and queen may be very similar to one another in most contexts, right? But it looks as though whatever document this was pulled from, maybe queen and woman go a little bit closer together and king and man go closer together. This is what is meant by vectorizers, looking at this picture to detect relationships that exist within the words in a body of text. Okay, and you're seeing that again here too. So common tasks in NLP, right? We just touched on a very, very, basic components of it, looking for relationships that exist. Things also like tokenization, so breaking your text up into individual constituent pieces. Part of speech tagging, so identifying whether something's a noun or a verb or something. Named entity recognition is where you sort of say, okay, what nouns am I identifying? Is this a person? Is this a place? Is this an organization, right? Text classification, so you could look at, say, tweets, things like that, and say, is this something that is a positive, sentiment or a negative sentiment? Many, many different things that can be done using NLP tasks. So just a very quick wrap up here. So Erica took us through the 7-step data science process, introduced us to supervised and unsupervised machine learning, and then my sections were a little more deeper dive into some AI algorithms and methods. And at this point, we would very much appreciate any feedback you have. So Anya, I don't know if you want to drop in the chat the survey. Thank you. The poll. Yep. So
Yeah, I think we have some polling questions. So if everybody can take a few minutes to answer the polling questions.
And then I'm gonna just plug really quickly here. So yeah, in the slides, we've got the summary there for you. And I'm gonna plug, we'll stick around for questions. I just want to plug really quickly as well. We do have some follow-up trainings as well. So on March 27th, if you're interested in learning more about artificial intelligence, going a little bit deeper into some of the topics that we talked about here today, we have part 1 of our AI Fundamentals course on March 27th, and on April 24th, part 2, AI Fundamentals part 2.
Yes, thank you. So I do want to, while we go through the polls, I want to take advantage and thank all of you for your attention, the participation from all of our attendants, and of course our experts that were here today, Erica and Dr. Aiello. So this was a great introductory session, I think, for our webinar series, and I hope that all of you that attended today learned something new or strengthened your awareness. And I hope that you all join us next month for our next session that will be, like he mentioned, about artificial intelligence, that will include some of the basics and some of the responsible uses, operations, and perhaps some of the implementations of AI. And that will be the March 27th, that will have the first session of AI Fundamentals, and April 24 for the second session of AI Fundamentals.